Hi, I'm Gregory Lee, and I'll be talking today about GPU acceleration for medical imaging and DIPY. I'll briefly cover some of the computational challenges, some of the tools for GPU computing in Python. I'll focus specifically on CuPy and how we accelerated some of the algorithms in DIPY using it, and then another separate software package built in C++ with wrappers for Python to do CUDA accelerated probabilistic tractography. So modern biological imaging methods, both in medical imaging and microscopy, are generating increasingly large data sets, and there's also a trend towards larger scale studies involving hundreds to thousands of participants. And in these cases, you have a large amount of data that it's really a challenge to process and analyze it efficiently. Just for context, I want to go over briefly what's meant by the term n-dimensional image processing. By n dimensions, I mean just an arbitrary number of dimensions. So it could be 2D, could be 3D, or more dimensions. So in the case of MRI, these may commonly be your Cartesian XYZ axes. You might have a dimension for time if it's a time-resolved experiment, or you may have other sort of channel dimensions where that may be, your B values and B vectors in a diffusionmri experiment, for example. So we'd like tools that can sort of handle this data of arbitrary number of dimensions and do things like apply filters on any subset of the axes. CuPy has an ND image module that's fairly good for this. Just a basic example shown in the last line here of applying a median filter to some 5D data variable here, where we've specified a 5 by 5 by 5 median filter along these first three axes, and then just set size to 1 along the other axes where we don't want to do any averaging. So popular existing n-dimensional image processing toolkits are ITK on the C++ side, and then in Python there's SciPy ND image, which is basically kind of the low-level filtering and morphology, things like this, with kind of higher level algorithms tend to be in the scikit image package, which is a separate Python project where a number of the bottlenecks are implemented in Python. ITK itself is pretty efficient on the CPU. It has better multiprocessing and things than the SciPy or scikit image libraries, but it really has very limited GPU support. And SciPy and scikit image themselves also do not have GPU support. So there are other libraries I should mention, like OpenCV, which are high performance. They have quite a bit of things implemented in CUDA for the GPU, but they're really focused only on 2D images and video, which makes them less interesting for volumetric medical imaging applications. So I want to go over briefly what the term general purpose GPU computing means, or GPGPU. You may see that acronym. This is referring to use of GPUs for general computing as opposed to just displaying video for like watching movies or playing video games and that sort of thing. So you can actually do a lot of computations on the GPU. Modern GPUs have thousands of computational cores. So you may have, an 8-core CPU on your desktop, but your GPU might have, say, 5,000 cores or something on that order. And so if you have a problem that can be kind of parallelized, or you can split things up across many workers that can be working independently, then you have a good chance of being able to really speed that up by more than an order of magnitude when running it on the GPU. And a number of image processing operations are good examples of that. Things just like thresholding, adding two images together, applying a filter where you're doing the same operation at every voxel, and you can just split those voxels up across the GPUs. And over the years, there have been a number of toolkits for doing this. NVIDIA has their CUDA toolkit, which is very good, but only available for NVIDIA GPUs. AMD has Radeon OpenCompute, and then the Khronos group has OpenCL and SYCL frameworks, and more recently Intel introduced this one API. Today I'm mainly going to focus on CUDA because that is the one that has the most mature tools in the Python space to be able to do the sort of things we're demonstrating here. CUDA stands for Compute Unified Device Architecture. The advantage of it are that it has a number of high-quality libraries for numerical computation, things like FFTs, sparse matrices, linear algebra, and so forth. It's been adopted by the majority of the popular machine learning frameworks like PyTorch, TensorFlow, MXNet, and so forth. You can use it from Python via various tools like CuPy, PyCUDA, NumPy, JAX, and so forth. There are GPU equivalents as well to some other packages like Pandas and scikit-learn that are provided through the NVIDIA Rapids group. The main disadvantage of CUDA is the core toolkit itself is closed source. Some components like these Rapids tools are open source, but the core CUDA toolkit and compiler are closed source, and it really only runs on NVIDIA hardware. OpenCL is another alternative. Its advantage is that it can run on a wider variety of hardware, and it's an open standard. It has some good numerical libraries, but not quite so many as CUDA, and some of the tools are made for use via Python, like PyOpenCL or Rakna for FFTs. The main disadvantages for OpenCL are that it's not been as widely adopted as CUDA, and there's currently no Python library based on it that really provides the sort of full NumPy API in a manner analogous to what CuPy does for the CUDA space. I just want to mention one other technology called HIP, which is basically something that AMD came up with, and it's kind of a higher level abstraction above both CUDA and AMD's Rokem toolkit. So basically you would write one set of code in HIP, and that could be dispatched to either CUDA or to AMD, so that if you're doing a C++ project and you want to support both of those manufacturers, you can do that from a common code base. And that's something that CuPy also is able to take advantage of and run things through these kind of AMD equivalent libraries for users with AMD cards. So some of the popular tools I already mentioned in the other slides. There's a lot of these deep learning frameworks like PyTorch and TensorFlow using CUDA, and really PyCUDA and CuPy let you kind of write your own kernels and compile these and do custom operations, and NumPy is in that space as well, where in NumPy's case you write something that looks like Python, but it converts it to kind of GPU code for you on the back end. Optionally, it can be CPU or GPU in the NumPy case. So why are we looking at CuPy specifically? One of the biggest advantages is it really closely follows the NumPy API, so pretty much the same way you would create arrays in NumPy or call various functions in NumPy. They use the same names, same arguments, and so forth. It just runs on the GPU instead of the CPU. It also has a smaller but useful subset of SciPy for things like sparse matrices, FFTs, special functions, and some of the in-dimensional image processing. I found it in general to have fewer surprising deviations in behavior than some of the other tensor array libraries. So now, PyTorch, JAX, and so forth also provide namespaces that kind of follow the NumPy API. I just found the CuPy one to be a little easier to get along with at the time that I had compared them. Powerful utilities exist in CuPy for creating Elementwise kernels and raw kernels from Python if the built-in functions don't already cover what you need. And it can also support AMD devices, despite the CUDA and the Q in CuPy being for CUDA. It does have some HIP Rokem backend support, at least in the upcoming version 9 of the library that'll be final in April. I should also mention I worked on many CuPy-based equivalents to scikit image functions in a CuPy image toolbox, and this will be moving to a new home in the Rapids organization later in April 2021, so there will be a talk on that at GCC this year. So basic CuPy usage, as I mentioned before, it looks basically exactly like NumPy, except you change from NumPy to CuPy for your imports, and when you call cupy.arange, you make a range of numbers in an array on the GPU, and you can do reshape, you can call square root and other functions just like you would in NumPy, the only real difference being that things are on the GPU. There are particular functions that will transfer a NumPy array to the GPU, or to transfer a GPU array back to the CPU, so it becomes a NumPy array again. So general tips for working with CuPy are that you want to minimize data transfers between the host and the GPU, so there's quite a bit of overhead in terms of the speed at which you're able to do that. NumPy will generally be faster if you're applying operations to very small arrays, like things that'll fit in the L1 or L2 cache of your CPU. And that's partly because there's some overhead when launching CUDA kernels. It's on the order of microseconds, whereas I think general Python function launch overhead is more like hundreds of nanoseconds. And generally, single precision runs at least twice as fast on GPUs as double. It may be an order of magnitude faster on some classes of cards. Mention briefly later that it's often also advantageous to fuse multiple mathematical operations into a single CUDA kernel, and that mainly is related to the kernel launch overhead I mentioned before. So some differences between CuPy and NumPy to be aware of. CUDA kernels launch asynchronously, so you'll have control returned to the CPU immediately after you call the computation. And so this can, it's not something you generally have to worry about too much in terms of explicitly calling synchronization and so forth when you're using this on the Python side. But if you're trying to time functions, you may not get an accurate measure if you don't take that into account. So there is a utility like this repeat function available in CuPy that will help you with that. Another difference that can be a little bit surprising at first is calling something like the sum over a whole array rather than returning a scalar value in NumPy. It remains as basically a zero-dimensional or single value array on the device itself, and that's mainly to avoid that overhead of transferring things back to the host unless needed. And there are some other subtle differences in kind of corner cases and indexing and things like that, which are documented on the website. So a couple other aspects of CuPy I wanted to cover were Elementwise kernels and fusion of basic CuPy operations into a single kernel. If we look at a function like the one on the left, if we ignore this decorator at the top at first, it's just kind of your standard Python function where you're taking in some image, some other variables that we want to subtract the mean, square the image, divide by 2 times the variance, exponentiation and square root and so forth, and basically return the result of that. If we do this in CuPy, each of these individual mathematical operations is going to be its own kind of GPU kernel or function that runs on the GPU. So it's going to be launching several separate functions, as opposed to if we add this decorator, this fuse decorator, it's saying we would like to combine all of those into a single GPU kernel. And CuPy has this utility or ability to do that in an automated fashion when everything in this function is kind of a basic mathematical operation, or a few of the reduction operations like sum and product I think are supported for that as well. Another option is to create your own Elementwise kernel. And here you would define what are the inputs to this kernel and what is the output. And here this W is some placeholder for the data type, saying that since it's the same character in all of these, they're all expected to have the same data type for the inputs and outputs. And all we have to write in terms of the C++ code is just what operation that would be applied to each element of these arrays in the inner loop. So this basically looks very much like this Python code over here, except now we're in C++. We need semicolons, and we need to call these C++ versions of these functions, where here these exponential and square root are actually the NVIDIA thrust library equivalents, which are templated C++ functions, so they can deal with various types of these inputs. So then you would define a function as before, but now you would dispatch to this kernel, and when CuPy sees the actual data type, it's going to generate concrete C++ code corresponding to that kernel send that to the NVIDIA real-time compiler, which will compile it and return a function that you can call from Python that corresponds to this kernel. So the very first time you call any given kernel takes a second or so to do the compilation, and then all subsequent times are fast because it loads it either from the in-memory cache or from disk. So I provided a few example notebooks to look through on kind of basic CuPy usage, some of this Elementwise and Fusion stuff, and interoperability between CuPy and other libraries. That concludes part 1.